Good morning, friends. Today's class 5 on classical mechanics, that is physics. Somewhere we have stopped discussing holonomic constraints. Almost we have completed the examples on holonomic constraints. Today we'll discuss non-holonomic constraints. Well, non-holonomic constraints are the constraints which can be expressed in the form of inequalities, can be expressed in the form of condition. The other definition or other way this non-holonomic constraint can be explained or defined as a non-holonomic system referred to a system which can be represented by non-integrable differential equation. I'll repeat, a non-holonomic system is said to be a non-holonomic if it is represented or expressed by non-integrable differential equation called as non-holonomic system or non-holonomic constraints. Somewhere we classify the system, a dynamical systems, as mechanical system or say a holonomic system and non-holonomic systems. In non-holonomic system, if it is represented by a non-integrable differential equation, then the system is called as non-holonomic system and the constraints are known as non-holonomic constraints. So here constraint, generally the other definition I will put before you. The constraints are the restriction on the freedom of motion. I'll repeat, the constraints are nothing but the restriction on the freedom of motion of a mechanical system. Well, non-holonomic constraints or constraints can be expressed in the form of inequality or a condition. We'll go for the examples of non-holonomic constraints. Let me explain example number 1. A particle moving on the surface of a sphere or outside the surface of a sphere. This problem can be put in other words. A particle moving on the surface of a sphere under the action of gravity. A particle moving on the surface of a sphere under the action of gravitational force. Say here is a sphere. This is a spherical body, not exactly a sphere, maybe a spherical body, and the particle is allowed to move on the surface of the sphere under the action of gravitational force or gravitational field here. As long as there are two parts in this example. Part number 1. As long as the particle is on the surface of the sphere, particle will roll or will slide on the surface of the sphere. Particle is allowed to move on the surface of the sphere. When the particle moves on the surface of the sphere, there is one case, and the other case when that particle leaves this surface When the particle falls out of the surface of a sphere, there is another condition. These two conditions put in one problem, that is a particle moving on the surface of a sphere or outside the sphere under the action of gravitational force. Well, this is a sphere of radius a and particle is represented by this P of x, y, z. P of x, y, z is the position vector of a particle P from the center of the sphere. We have fixed a coordinate system at the center of the sphere. This is, say, y, this is z, this is x. This x, y, z coordinates we can write in any way, not necessarily we can write this as x, this as, say, y, and this as z. I have written here this as x, this as y, and this as z, any one direction. Okay. Particle is allowed to move on the surface of a sphere, and the sphere is having a radius a. A is the radius and p is the position of the particle at a given instant of time t. Well, O is the center at which we have fixed a coordinate system, rectangular coordinate system or a Cartesian coordinate system. Well, O is the center. Theta is the angle met by the radius vector A here. Phi is the angle between, say, the y and x axis. As long as particle is on the surface of a sphere, we represent the constraint is this x square, that constraint equation x square plus y square plus z square is greater than or equal to a square, where a is the radius of the given sphere. Here, when we take the square of this, I can write the position of this particle in terms of a position vector. R is the position vector. R may not be equal to or all the time equal to radius. Same example we have considered in case of polynomic constraint, where R is equal to the radius, that is the position vector of a particle is equal to the radius of the sphere. Here R, the position vector of the particle, say this particle P at given instant, it is here at equal to a distance, say distance equal to its radius. The particle may slide down. Particle may move on the surface or slide down. Say in this way, particle is moving on this surface and say slides down. So when it leaves the surface, so the radius or the position vector R may not be equal to the radius of the sphere. Position vector R from the center of origin, from the center of coordinate system is greater than or equal to radius of the sphere. Therefore, we have written x square plus y square plus z square, which is greater than or equal to a square. This is an inequality. It is not equation. It is an inequality. This quantity is greater than or equal to, there are two possibilities, greater or equal to a, the radius of the sphere. If this is represented by R called as a position vector using distance formula, R square is greater than equal to a square. Right? It is equal to a square when the particle is on the sphere. I have written this x square plus y square plus z square is equal to a square. One, or as long as particle is in contact with the sphere. When particle is in contact with the sphere, we can write this. We have done this before. R square minus a square is equal to 0. This is equation. r minus a is equal to 0. When r is equal to a, this becomes 0. That variable becomes independent. One variable we have removed. That we have discussed in earlier examples. Here, as long as the particle is on the surface of the sphere, this is true. Fine. When the particle leaves the surface of a sphere, this will. That means this a particle rolling or moving on the surface of a sphere under gravitational force is an example of non-holonomic constraint, because we can express the constraint in the form of inequality. When the particle leaves the surface of a sphere, we have this x square plus y square plus z square is greater than equal to a square, or r square is greater than a square, or r minus a is greater than 0. Well, there are two cases here. Particle is allowed to move either on the sphere or outside the sphere. This is common example quoted in all the books as a non-holonomic constraint. But if you understood this, we'll take a common example known to you. I'll make use of this space. That is second example. A gas molecules in the container. In very first theory class, I have discussed this under an article called as constraint. When gas is enclosed in a container, right, and say it is closed, we know, as per according to gas laws, gas molecule cannot be brought at rest. All the time, gas molecules are in motion, and its motion is called as a random motion. So particle of the gas, they move, they collide, they move up and down, whatever possible say position or a direction, gas molecule can take that. So the gas molecule, they can move only within the walls of the container. Imagine we have a container and say the container is spherical in shape. Container is spherical in shape, and say the gas molecules are the dots represents the gas molecules. This is enclosure, a gas container, spherical in shape, and say it is closed, and the gas is enclosed in it. As in case of a balloon, when we blow a balloon with air and when we close it, it may not be exactly spherical, but it is round and closed. Now the air inside, air are the molecules, gas molecules, different gas molecules. Those gas molecules, they are not at rest, they are in motion. Their motion is random. All the molecules in the enclosure here, a container, they are allowed to move well within the boundary of this container. Then it collides with the walls of the container. At a given instant, if I fix a coordinate system at the center, say this is coordinate system, you can call this as say y, you can call this as z, say this is x. Now, O is the origin. It is imaginary thing, the coordinate system. Now I want to locate the position of a particle P. This is particle P. So R is its position vector. Suppose this is a spherical body, a circular body. Assume its radius is A. Its shape doesn't change here. We'll assume that shape of this container in which gas is enclosed is its radius A. This is A is its radius. Fine. A is the radius. and this is the position vector. As per this example, I can write x square plus y square plus z square is less than or equal to a square. Gas molecule here, in this case, they are not allowed to go outside the container. So, if I write this is r square, the position vector which is less than or equal to a square. A is the radius of the spherical container, gas container. Say for example, a balloon or a ball which is spherical. Right? So, r square minus a square is less than or equal to 0 when the gas molecule's is in contact with the wall of the container. R square minus a square will be equal to 0. A square will be 0 when gas molecule is well within the container somewhere here, well inside, where the position vector is smaller than its radius of the container. R is, say, r minus a square is less than 0. There are two possibilities. Inequality. So this example belongs to a holonomic system, and the constraint are holonomic constraint. This is second example which we have here. Let me go for another example called as, I'll rub this now. Another example, say rolling disc. Fine. Rolling disc. I'll write this as the example number 3. Rolling disc, a non-holonomic system. Holonomic system or constraint. Fine. Well, I have drawn here the figure. I have already drawn it because it takes time to draw it. Imagine a disc here is rolling on a rough xy plane. The constraint on this rolling disc is, this is our x-axis, this is z-axis, and this I have represented as y-axis. Anything which may be go down. Normally we draw only 3 positive axis only, x, y and z. It may go this way, this is negative. Okay, y, this is x, this is. Fine. So I have drawn. So this system is, coordinate system is adjusted or taken as per the convenience of a person who is solving this. Well, this is coordinate system x, z and y. This is a disc rolling on a rough vertical xy plane. So this is x parallel to this. This is O, you can say, parallel to x-axis. It is x, and this disc is rolling in the xy plane. Constraint is that this disc should be always vertical. It should roll on a vertical way. So that means its disc should be always vertical, and the axis of the disc is always perpendicular to z-axis here. So this is axis, the disc is rolling, and then it is perpendicular to z-axis. We have fixed x and y coordinates, at the center of disc. Here phi is the angle between the direction of rolling and x-axis. Okay, this is phi. Theta is phi is the angle here. Theta is the angle between axis of the disk, there's an axis of the disk and the x direction here. So we have drawn this. When this disk is rolling, it is rolling with certain velocity. Fine. So what is the constraint here? The axis of the rolling disk should be always perpendicular to the vertical axis, that is z axis, along which this disk is rolling. Let v be the velocity of the disk. V be the velocity of the disk. Theta is the angle here. Okay, and this is point P. Say this is point Q. Okay, P, Q, C is the center here, and x-axis 90 minus theta, because this velocity is assumed to be perpendicular to the z-axis. So I have redrawn this. This is figure 1 or figure A, and say this is figure 2. Hope you got this. Say B. Fine. This is the axis of the disk. We have drawn this, which makes an angle theta with x-axis. Right. Now this is V, which is perpendicular to the z-axis. This is V is the velocity of the rolling disk. So according to the geometry, this is y-axis here, this is x-axis. If this is theta, this will be theta. If this angle is 90 minus theta, because it is perpendicular, 90, this minus theta with y-axis, here this will be 90 minus theta. Now the question is, if A is the radius of the rolling disk, this, then the velocity V is, I have written here, V is equal to radius times the angle, that is dot A. Now we have come across a point where this should be remembered and you should note here. If I write any letter, say X and then dot on its head, this indicates, as per differentiation, dx by dt, that is first derivative of the variable x. If I write x double dot Mickey Mouse, I can write this is equal to d square x by dt square. Keep in mind, this is the notation we are going to use in all the future classes. So phi dot is d phi by dt, the time derivative of this variable, that is the angle here. Phi is the angle, angle of rotation about the axis of the disk. Phi is the angle of the rotation about the axis of the disk which is rolling. So V, the velocity, that is normally we take A, the radius, R theta, that is R, say R phi dot. If I write this as A d phi by dt, the velocity which we have indicated here. Now the velocity is not directing, not a particular direction either along x-axis or y-axis or z-axis. We should, because it is a vector quantity, we know how to resolve it. The x component of this velocity, Vx, that is dx by dt. Vx is dx by dt and it is v sine theta. Similarly, we have y component of the velocity v, that is v is equal to dy by dt, that is minus v cos theta. So using this v, let me substitute v is equal to a d phi by dt or a phi dot. When I say a phi dot, that is dot should be on the head and it should be read as d phi by dt or any variable, d dt of that variable, that is derivative with respect to time of that variable. So we got Vx, we got Vy. Vx and Vy are the component velocities or component of the velocity of the disk. We are discussing rolling disk as a non-holonomic system or a constraint. Fine. Well, so I want to find the dx by dt. Dx by dt, that is Vx, is equal to a d phi by dt sine theta. Right? We have substituted the value of v. Similarly, dy by dt is equal to minus a d phi by dt cos theta. If we eliminate this dt on both sides, we have this. This is all. I can write this as dx minus, say here, a d phi sine theta is equal to 0. dy minus a, this is plus d phi cos theta, which is equal to 0. Now, you may come across this equation, we got this equation. Now this equation tells us that we cannot integrate these equations unless we solve the entire problem. That means a holonomic system or a constraint is the constraint which can be represented by non-integrable differential equation. We have here d phi by dt. This cannot be integrated because to integrate this, we have to solve the entire problem. We cannot integrate this non-integrable differential equation. And therefore, a rolling disk vertically in the xy plane is an example of non-holonomic constraint. This example they quote in almost in all the books on classical mechanics, and we have come across rolling of a disk. We have come across another example of, say, inclined plane, right? The inclined plane example is not non-holonomic, say this is inclined plane, and roller is rolling on this. Roller is rolling on this. Many times we have played a game on such a place, okay, rolling. So when its body is rolling on this in an inclined plane, this happens to be, it gives a simple equation and it happens to be an example of holonomic constraint. Leave it. If time permits, we'll discuss it. So far what we have discussed is, let me summarize. We have discussed constraints, are nothing but the restriction imposed on the freedom of motion of a system of particles. Constraints are nothing but the geometrical restriction on the freedom of motion of system of particles is known as constraint, and the motion of that system is called as constraint motion. When we have constraint motion, for this constraint motion or constraints in general are classified broadly into two. One is holonomic constraint, integrable in the form of which can be represented. Holonomic constraints are the constraints which can be integrable. Equations can be easily integrable, so we call them as holonomic. And non-holonomic constraints are the constraints which can be represented by inequality, a condition, or represented by non-integrable differential equation. When we have written a general equation of constraints, I'll write once again f of I, x1, y1, z1, x2, y2, z2. Say xn, x3 or so on. Say xn, yn, zn and t, which is equal to 0. This is general equation of a holonomic constraint. If there are n number of particles in the system, so the particles can be represented by number of coordinates. There are n number of 3n number of coordinates required. Here we have a time. If the constraints are dependent or varies with time, we call those constraints are time dependent and time independent. Now the time has come to classify constraints further into two types, depending on whether the constraints are dependent on time or independent of time, known as, say, celeronomic and rheonomic constraint. SC LE celeronomic